Right, I have here a couple of problems based on ray optics, which is chapter 34 in your textbook. And these problems are kind of conceptual problems or simple calculation type of problems. So let's take a look at the first one, number 4. It says a light beam passing from medium 2 to medium 1 is refracted as shown in the figure. Is N1 larger than N2, or is it smaller? Or is there not enough information to tell? So we can see a sort of a red light ray going from incident at the interface between medium 2 and medium 1. So it's coming from medium 2, hits the boundary, changes direction. That's called refraction. And we can see there in how it changed direction. And based on that picture, they're asking us if we can tell which n index of refraction is bigger, N2 or N1. So first thing that we need to do is draw the normal, because remember that the equation that applies for refraction is Snell's law, and Snell's law measures or deals with the angles of incidence and refraction as measured from the normal, that is a perpendicular line to the interface. So we draw the perpendicular line to the interface. The angles are indicated there. Theta 1, I'm going to call it the angle of refraction in this case. Theta 2 is the angle of incidence. And what Snell's law says is that N2 times the sine of theta 2 is equal to N1 times the sine of theta 1. So we can see in the picture clearly that theta 2 is less than theta 1. The angle of incidence seems much smaller than the angle of refraction. So because theta 2 is smaller than theta 1, that means that the sine of theta 2 is smaller than the sine of theta 1. This forces N2 to be bigger than N1, because the product of N2 and the sine of theta 2 must be equal to the product of N1 times the sine of theta 1. So if sine of theta 2 is less than the sine of theta 1, then it must be true that the N2 must be bigger than N1. Alright, so we conclude from the picture that N2 has to be bigger than N1. So the light ray is going from a high index of refraction to a low index of refraction. Alright, let's take a look at the problem number 5. It says that a fish in an aquarium with flat sides looks out at a hungry cat. To the fish, does the distance to the cat appear to be less than the actual distance, the same as the actual distance, or more than the actual distance? Explain. Alright, so we dealt with this problem in a video. So here we have an aquarium. There is a fish inside the aquarium. There is a cat outside. And we are looking at the cat from the point of view of the fish. That's what it says. To the fish, does the distance appear, blah, blah, blah. So that is the fish, the one that's going to be the observer here. The object here is going to be the cat. So we are wondering, the question is about where is the image of the cat going to be located according to the fish. Is it going to be in front of the cat, that is closer, or is it going to be further away? Or maybe at the same location as where the cat is. So the equation that we discussed back in that video was an equation that is easy to remember, is NOSO equals NISI. So the NO refers to the index of refraction of the medium where the observer is. So the fish is playing the role of observer in this problem. So the index of refraction of the medium where the fish lives is, of course, water, so it's 1.33. The SO in the equation refers to the distance to the object, in this case the cat. The N sub I refers to the index of refraction where the image is going to be located. So that's going to be the air, that's where the cat is. So air has an index of refraction of 1, or very close to 1. And the SI is going to represent the distance to the image of the cat, wherever the image is going to be located. We'll see from the equation where we can conclude that the cat's image is going to be located. For now, we just call it S sub I, and we'll see what happens. So replacing the numbers in the equation, N sub O is 1.33 times SO equals 1, N sub I is 1, times S sub I. So the equation says that S sub I is 1.33 times SO. So clearly that means that the distance to the image of the cat is bigger than the distance to the cat itself. That distance is measured from the interface. So that means that the cat is going to seem to the fish, the cat is going to seem further away than it actually is. So the image of the cat should be located behind the actual cat. Alright, that's all I have for now. I'll see you in the next video.